Now let's talk about the comparison test. So as a motivating example, consider the sum from k equals 1 to infinity of 2 plus the sine of k divided by k. And our question here is, does this series converge? So what we can do is kind of reflect on what we've seen so far to try to see how that stacks up. So the first question is, or not the first question, the first thing to consider is the definition. So we've seen that the definition of convergence is that the limit of the partial sums exists and is finite. And in order to use this, we needed to be able to come up with a closed form expression for the nth partial sum. And we saw that this was particularly useful when we had telescoping and geometric series. Because in both of these cases, we could find a formula for the nth partial sum. So that's kind of a quick recap. Now, considering that, if we look at this particular example, it's not going to be geometric and it's not going to be telescoping. It doesn't fit those forms. So, doesn't work here. So then another thing to consider was the test for divergence. So in that case, we look at the limit of the terms. So here I would look at, so maybe I'll write first that the test for divergence says that if the terms do not go to zero, the series diverges. So for us, so here, if I take the limit as k approaches infinity of a sub k, that says what's the limit as k approaches infinity of 2 plus sine of k divided by k. Notice that the top is bounded, right? It's bounded between 1 and 3, but the bottom grows without bound. So this limit is 0. So remember that when the terms go to 0, we get no information from the test for divergence. And the only other thing we've seen is the integral test. And for that, we said that we could consider the connection that our a sub k is equal to f of k on whatever our interval is, let's say 1 to infinity, and we want to suppose f of x is positive, decreasing, and continuous. If that's true, then we can say that the sum of the a sub k's and the integral of f of x both converge or both diverge. Now, what we want to look at here is, again, what can we say? And I'll point out that the sine 2 plus sine of k over k is not always decreasing. So we can't use the integral test on that. So what we've done here is I've done just a recap of what we've seen so far. Those are kind of the bulleted points. And then what I've done beyond that is that under each bullet point, we've paused to see how that corresponds to this particular example. So what we've seen is this example is something that we could not handle with what we've seen so far. Turns out it's a perfect example for what's called the comparison test. And let me write up what the comparison test is, and then we'll come back and use it on that particular example. So there is the comparison test for integrals. So I could compare two improper integrals. Technically, you could think about the integral test as a way of comparing an integral in a series. And here, when we talk about a comparison test for series, it's a way of comparing two series. So the premise is very similar to what we've seen in making similar comparisons before. I have to suppose that I have positive terms. So I have two series, a sub k and b sub k, both of which are always positive. And beyond that, let's assume that a sub k is always less than or equal to b sub k. Then there are two potential things we could say. If the sum of a sub k, the smaller terms, diverges, then the sum of the b sub k's likewise diverges. On the other hand, if the sum of the b sub k's, the larger terms, converges, then the sum of the smaller terms converges as well. So these are going to be the two useful conclusions we could make here. We'll come back to this later, but knowing that the sum of the a sub k's converges, or alternatively that the sum of the b sub k's diverges, would actually give us no information. Now, given this test, let's go back to our original example here. So if you recall, we were stumped on looking at the sum from 1 to infinity of 2 plus sine of k divided by k. So one of the things I referenced when we were talking about the limit before is that we know that sine of k is always between minus 1 and 1. So that tells me that 2 plus sine of k is always between 1 and 3. And then what that means for my terms is that if I look at 2 plus sine of k over k, that is greater than 1 over k and smaller than 3 over k. So we have both a lower and an upper bound here. We have to think about what kind of comparison is useful. Notice that both of these having this 1 over k remind me of p-series. And we know that a p-series where you have 1 over k to the p equals 1 would diverge. So the sum of the terms on the left would diverge, and then essentially the one on the right is 3 times that sum, and that would also diverge. So it's really going to be this comparison that is useful here. If we can show that the lower bound on this sum diverges. Knowing the upper bound diverges doesn't tell us anything. So what I can say here is that my sum of interest is greater than or equal to the sum of 1 over k, which diverges. And so we're going to have several layers here where it's really going to be important to justify this. So when I say that the second sum diverges, I need to say why. And something like a quick note that it's a p-series with p equals 1 is a justification that this series diverges. So by showing that our series is larger than that series that diverges, so the one that we are focusing on diverges as well. And again, I have to justify why this one diverges, and that's the comparison test. and I'll put that as by CT. So the interesting thing I think about the comparison test is that it's relatively simple to understand if we just think about the relationship between these terms and what convergence and divergence mean. By contrast, you can think about the integral test. That was kind of hard to understand. We had to consider all these pictures and think about why we could relate those two things. But once we applied the integral test, it was very clear that we integrate a function, we knew what bounds, and so it was a little bit more straightforward to apply. The comparison test, while maybe simple to understand, is a little bit hard to apply because we have to know when to use it, of course, but also once I decide to use the comparison test, I need to come up with a suitable comparison that will lead to a valuable conclusion. So that's going to be something that really, the more examples you do, the easier that becomes. In the next video, I want to focus on several examples where we tried to build up some of that intuition about how to come up with the best comparison to make.